Okay, so if there is nobody has a question about that, we will go ahead and start. If I can figure out how to work this. Go. All right. So what we're going to talk about today, like I said a minute ago, is very much kind of a continuation on this theme of long-run economic growth. In my humble opinion, I think that's probably the most important topic to study in a macro principles course. What did we learn in the last chapter, last section of the course? We talked a lot about productivity. How do we quantify or measure productivity? It's the amount of output that a country produces per unit of labor. And it was increases in worker productivity, which is what we identified would tend to drive improvements in a country's standard of living in the long run. We also spent quite a bit of time talking about some of the underlying features that make workers more productive. And we highlighted 3 of them in particular, right? Physical capital, human capital, as well as technological progress. And we also spent a little time talking about various policies and some key institutions that are important for countries to experience growth in living standards at all. All right, so hopefully you guys understand that stuff and can, if not, can go back and review it on your own. All of those ideas, concepts are important, but if you really think about it, it's really nothing more than kind of a loose set of ideas about economic growth, all right? What we want to start doing today is trying to formalize this discussion of economic growth using what I will describe as a coherent macroeconomic model, okay? Now, if we try to characterize the growth process using kind of a fully articulated model of the economy, that has 2 big benefits for us, all right? Number 1 is I think it's going to help us really organize our thinking about what the key forces in the economy that are responsible for improvements in living standards and growth over time. It's a way to help us kind of organize how we think about those types of things. The second important benefit of using a coherent model is that only with a model, particularly one that we can kind of quantify, assign specific numerical values to, can you ever hope to really be able to provide any type of policy guidance, right? Suppose the government commissions a study and asks something like, how would a change in the tax code affect productivity and standards of living 10 years down the road, or even 20 years down the road? Or alternatively, how would a big investment by the government in research and development improve living standards over time? Well, you can't really hope to provide any concrete answers to those types of policy questions in the absence of a formal model. We need something more than these loose set of ideas that we've talked about so far: productivity, capital, technology, etc. Can we put all of these items together, these ideas together, in something that actually resembles a more sophisticated economic model? The answer to that question is yes, and it's what we're going to start doing today. Now, the growth model that we're going to talk about is called the Solow Growth Model. That is not named after Han Solo or some other Star Wars character. That is named after Robert Solow, the economist who first developed this growth model way back in the, I think it was actually the late 1950s. He won the Nobel Prize in economics sometime in the 1970s for his contributions to economic growth. This model, although it is simple and simple enough for undergraduate students to understand, really forms the basis or the foundation for a lot of the very complicated macroeconomic models that are studied and researched today. So it's an extremely important growth model. Now, let me just give a quick word of caution before we start getting into the details of this model. What we're about to cover in this class is a bit more advanced than what a standard macro principles course would go through. If you were taking, this is an honors course, if you were taking the kind of the regular principles 111, I think it is, most likely you wouldn't cover this. And a lot of times students don't see the Solow growth model actually until they're in intermediate macroeconomics. I've had a lot of success teaching it in this class over the years because I try to present a very streamlined version of it. And so we're going to do that, but I just want to caution you ahead of time that the math, really more the graphical analysis and some of the concepts are a bit more advanced, a little bit more sophisticated than what you're going to see in the rest of this course, okay? In fact, the Solow growth model is not actually discussed in your textbook at all. So the readings for this, if you'll notice on the syllabus, come from a supplemental source that I've Xeroxed and put on Blackboard. So if you want some further background reading on it, you'll have to go elsewhere from your textbook, okay? But I'm confident that you guys can handle it if we kind of go through it slowly and explain everything clearly step by step, okay? So there's no reason to panic here. Okay, let's go ahead and get started then. So to help us kind of motivate the development of this model today, let me give you guys some quick statistics that should help illustrate some of these key concepts a little bit better. In fact, a lot of this I think you already know because we covered it a little bit in the last chapter. In 2019, China's per capita real GDP grew by 5.7%. The United States per capita real GDP, however, only grew by 1.8% last year. Now, of course, this was just for 2019, but this big discrepancy between China and the US, as you guys remembered from the last chapter, has been persisting for several years now. China has been growing much more rapidly than the United States for at least the past 20 to 30 years. In fact, the United States has rarely grown as fast as China is growing currently. So you have to look farther back into our history and at certain dates over time where we've even grown at rates that are close or similar to what China is experiencing recently. Okay, so all of this kind of raises some natural questions. One, how can this be true? Do these differences in how quickly we're growing tell us that there's something wrong with the US economy? Is there something dysfunctional about the United States that prevents us from being able to grow our living standards as rapidly as China? We're richer than China on a per capita basis, but it's undeniable that they're growing more quickly than we are. Or do the Chinese have some magical potion for growth? Do they know something that we don't know about the economic growth process? Okay. In fact, if you go and take a look at the data on those key growth institutions that I talked about in the last class, so what do we have? Political stability, a dependable court system, an honest government, the protection of private property. The United States actually ranks higher than China in all of those key growth institutions that we talked about as being really important for experiencing higher living standards over time. So why the heck is it that China seems to have figured out something that we don't know? Why are they growing so much more quickly than we are? These are rhetorical questions. I don't want you to try to answer yet. We're going to hopefully answer these questions before the end of today. Okay. To answer or shed some light on this mystery about why the Chinese economy is growing much more rapidly than the US economy. It's super important that you guys be able to distinguish between two different types of economic growth, okay? One of those types of growth is what's commonly referred to as catch-up growth in the economic literature, okay? The other goes by a lot of different names, but I kind of describe it as what we call frontier growth. So there's catch-up economic growth versus frontier economic growth. Now let me take a few minutes to describe the differences between those two concepts. Turns out that catch-up growth is easier than frontier growth to some extent. If you think about it, to become a rich country, or just to, if it's a poor country that is trying to grow its living standards over time, poor countries don't really need to develop new technologies and ideas to improve their productivity and their living standards. Really, all they have to do, and I say all they have to do to make it sound like it's easy, it's not necessarily super easy, but it's easier than frontier growth. What they need to do is more or less adopt the technologies and ideas about the production process that have already been developed and are already being practiced in the developed world, right? I know I was flying through this at the end of the last class, but technology is very much a public good. One country's use of a technology or a certain idea about production practices doesn't mean that other countries can't also use those same basic ideas. So one way for poor countries to get rich over time is to kind of mimic those ideas and technologies that have already been implemented in the developed world. That's what we mean by catch-up growth. And that's the sense in which it's easier than frontier growth. Now, what is frontier growth? This growth is more difficult, okay? Countries that are at the frontier of their growth trajectory, rather than in this kind of catch-up phase, only really grow over time, only really have higher standards of living per capita to the extent that these countries develop and put into practice new technologies and new production ideas, okay? The reason, I think, why a country like China, and I'm not necessarily picking on China here, I'm just using it as an example, but the reason why China has grown much more quickly than the US is because China is in the catch-up phase of its growth profile over time. India is another example of a country that's sort of in the catch-up phase and has also been growing more quickly than the US if you look at the data. The United States, however, is beyond that point in its development and is way out here on the frontier. Now, as we're going to describe throughout class today, this catch-up growth is really mostly about the accumulation of capital, both physical and human capital over time, okay? Countries that are in the catch-up phase of growth can simply adopt technologies that already exist in these frontier countries. And what they do is they try to accumulate physical capital rapidly over time. And that enables those countries to experience high levels of growth and therefore higher and higher living standards, right? And so even then, small investments in capital can generate large growth experiences for these countries that are adopting technologies that have already been developed elsewhere, okay? That's the sense in which catch-up growth is easier or faster. Frontier growth, again, is much more difficult. Frontier growth, let me emphasize this, is really not about accumulating more capital over time. Yes, it is true that the US economy adds to its stock of capital every year, but that's really not why we're getting richer as a society. The reason why US workers are becoming more productive over time is because we are developing new technologies and ideas. This is harder to do. It occurs in kind of fits and starts, right? And so growth at the frontier is naturally going to be slower and more difficult to accomplish, okay? The big goal here is to try to develop a coherent macroeconomic model that can distinguish or discriminate, let's say, between these two types of growth. Can we put together the pieces of the model that will help us organize our thinking about catch-up growth versus this frontier growth, and thereby help us kind of resolve this so-called Chinese miracle? Now, I use China as an example, but if you actually take a look at what's happening in China in very recent years, you will see that China's growth rates have already started to slow down, okay? So in fact, there's some evidence here that China is actually closer now to the frontier than they used to be, where their growth rates won't be so high. Okay, any questions then so far? All right, so the Solow Growth Model has 3 or 4 components, or let's say ingredients to them, that we need to put together. All right, so what I want to do now for the next several minutes is start talking about each of those ingredients separately. The most important one to the Solow model is something called the production function. Sometimes it's referred to as the neoclassical production function. I'm not sure if you've ever been exposed to this idea, so let me describe what it is. A production function, essentially, it expresses the specific relationship between a country's level of output or income, which we denote with a variable y, and the country's underlying factors of production. There are 3 factors of production I want to mention, but then in the discussion of this model, we're really just going to focus on one of them today. The first one is a country's stock of physical capital, which you may recall we denoted with the variable K. That's plants, equipment, machinery, warehouses, factories, etc. The second factor of production is human capital, which we talked a lot about. Now, how are we going to define human capital in the context of our production function? Human capital is going to be defined as the number of workers we have, or the supply of labor, so that's denoted L, times the education or the skill level of the average worker. So E times L tells us kind of what our stock of human capital is, as opposed to physical capital. The third factor of production is knowledge or technology. And I'm just going to denote that kind of generically with the variable A. In the next class, we will do an example of how we can kind of quantify an increase in technology by assigning specific numbers to it. What the production function tells us is how a country's level of output is a function F of these 3 arguments: physical capital, human capital, and technology. Now, for those of you who have never seen anything like this, I'm not sure how many of you have, this may seem a little strange, right? Usually we think of a production function as existing at the level of an individual business or a firm, right? So let's take our Mercedes plant down the road here in Tuscaloosa. Y would be the number of automobiles that come off the assembly line, right? That's the output of the plant. K would be the stock of equipment they have, including the warehouses and the factories there, the assembly factories. EL would be the number of workers times the skill level of each employee at Mercedes, and A would be the technology, their understanding about how to best assemble those automobiles, okay? This production function would then tell us how the factors of production are related to the flow of new autos, let's say every year. We're going to have several assumptions about the Solow model that I'm not going to explicitly put on the slides, but that I'm going to talk briefly about as we go through class today. The first assumption I want to emphasize here is that we are going to assume that the economy as a whole has a common production function. Okay, so you can think of this as, you know, all the different businesses in our economy have a pretty similar type production function. If we somehow aggregate those all together, you get an economy-wide production function, which tells us how our GDP, or total output, is a function of all of the capital, human capital, and technology together. That's the first key assumption. Okay, the second assumption that I want to make is that for the time being, I want to actually ignore the potential effects of changes in technology as well as human capital on the level of output. I'm not saying they're not important, but what I want to do is I want to assume that these guys here are kind of fixed and constant, all right? That's going to enable us to focus on physical capital as the key driver of real output over time. That's the feature of the model that helps us explain catch-up growth. If we take a country like China or India that is accumulating physical capital rapidly over time, they're also increasing their level of real output or income over time. Later on, we can talk about how changes in some of these other factors would cause the production function to shift or change, and how that can affect a country's growth experience or growth rate. But for right now, we're going to assume that these things are fixed and just focus on the relationship between physical capital and output. Okay, any questions yet? Are you sure? All right, let me talk a little bit about some important terminology with regards to the production function. So it's some terminology that reflects concepts that are extremely important to the Solow growth model. Okay, the one I want to talk about here is what's called the marginal product of capital. I'm going to denote it NP subscript K here, the marginal product of capital. Now, what is that? The marginal product of capital is defined as, it tells us how much extra output a country is going to achieve for each additional unit of capital that it produces. It's very similar to the microeconomic concept of marginal utility of consumption, right? Sam, if I give you an extra $1, how much additional utility are you going to enjoy as a result of that? That's the marginal utility of consumption, okay? The marginal product of capital is how much additional output we get from our production function for each extra unit of capital that we acquire. Physical capital, that is. Here's our silly little example that I have in my notes here. You take a cook at a restaurant who is equipped with, let's say, 1 grill. That cook can, let's say, grill 5 steaks per hour. If we arm that same cook with a second grill, let's say that he can make 8 steaks per hour. What would be the marginal product then of the second grill? 8 steaks minus 5 steaks gives us 3 steaks, right? So the cook here can prepare 3 additional steaks from the 1 extra unit of capital here, in this case, a grill for the kitchen. All right, assumption number 3, and again, I'm just kind of put this in the margin of your paper because I don't have this specifically spelled out everywhere in the slides, but we're going to assume that the marginal product of capital is diminishing. In other words, the production function exhibits the property of diminishing marginal returns, or sometimes it's referred to as diminishing marginal product of capital. Okay, So in my cook example, what was the marginal product of the first grill? Presumably you can't grill any steaks with 0 grills, right? So the marginal product of the first one was 5 steaks. What was the marginal product of the second grill? It was 3 steaks, right? So for each additional unit of capital, the extra units of output that are produced get smaller and smaller. That's what we mean by diminishing returns to capital. It will be crucially important to assume that the production function exhibits diminishing returns to capital in this Solow growth model. That's a key assumption in the model. I want you guys to try to better visualize what we mean by the marginal product of capital, as well as kind of the full nature of the relationship between the capital stock and output on the next slide. And so what I want to do is actually graph a specific production function, one that is used commonly in simple macro applications, okay? And so the function f that we just generically defined on the last slide, let me specifically assume that it's the square root function. So a country's output here is going to be assumed to be the square root of its capital stock. All right, what I want to do on the next slide is actually graph that so you guys can get a better feel for the full implications of the production function. Okay, so to graph that, we're going to place different potential values of capital on the horizontal axis and different possible levels of output then on the vertical axis. All right, here's what the production function looks like. Y is equal to the square root of the capital stock. So for example, if our economy only has 1 unit of capital, how much output are we going to produce? Well, square root of 1 is 1, right? So we produce 1 unit of output. Alternatively, if we have a lot more capital, let's say we have 9 units of capital, then how much output do we produce? The square root of 9 is 3, okay? In other words, what the production function shows us here is for a given value of capital, how much output our country is going, or our economy is going to produce. Okay, there are 3 points I want to emphasize about this graph before we move on to the next slide. The first one, you will notice that the production function as we've drawn it here just shows the relationship between output and physical capital. As we've drawn this production function, we've assumed that human capital and technology are fixed and constant. What do you imagine is going to happen to this production function if human capital or technology suddenly improves? In other words, it's not fixed. What do you think would happen to the production function? What happens to so if you look at a demand schedule, as the price of the good changes, you move along a fixed demand curve. Just as if we change the capital stock, you move along this fixed production function. But what if you change one of those other things that affects demand, like income or the price of a related good? What do we know happens to the demand curve, Sean? It shifts, right? The production function is also going to shift if one of those other factors that we've held constant suddenly changes. So remember that for the next class. If there's an improvement in technology, that's going to actually shift up the production function, meaning that we get more output for every unit of capital that we have. The second feature of the production function I want to focus on is this fact that the production function is increasing. You will notice here that as capital grows, output gets higher and higher. So the slope of the production function is everywhere positive. The last thing is that as the capital stock increases, what do you notice happening to the marginal product of capital? It decreases, right? What's the marginal product of the first unit of capital here? It's equal to 1. We get 1 unit of output for the first unit of capital. What is the marginal product of the 10th unit of capital? Output only goes from 3 to 3.2 as we've increased the capital stock by 1 unit, and so the marginal product of capital is 0.2. So the marginal product of capital is diminishing as the capital stock grows. That's the law of diminishing returns, or the law of diminishing marginal product. It's reflected in the fact that the production function here has this kind of concave shape to it. All right? So this production function satisfies the property of diminishing returns. Wyatt? In truth, yes. I've approximated it here by just going one unit at a time. So Wyatt brings up a good point. For those of you who've taken some calculus, what feature of the production function is synonymous with or is equivalent to this idea of the marginal product of capital? It's the first derivative of the production function. That is the slope of the tangent line at whatever value of capital we have, right? Wyatt, what feature, what concept from calculus then reflects the idea of diminishing returns? He doesn't know. Who knows? Does anybody know? I'm not going to test you on calculus, but for some of you who've had it, maybe this will provide you with better intuition. What's your name again? Say it again. Go ahead. So the second derivative is negative, right? The second derivative of the production function is negative, which means that the first derivative, or the slope of the production function, is getting smaller and smaller and smaller as the capital stock rises, right? The fact that the marginal product of capital is positive reflects the positive first derivative of the production function. That means output is increasing in capital. The second derivative being negative means that the production function is strictly concave. That is equivalent to saying that it exhibits diminishing returns to capital. Very good. Okay. Sorry. Does this property of diminishing returns in particular help explain this so-called Chinese miracle? Can we appeal to the law of diminishing returns to go a long way towards explaining why China has been growing so much more quickly than the United States? Sean? Yeah, whatever the slope is, it's going to be higher, right? So I think that's a good way to think about it. Think about this. In poor countries that have a low stock of capital, and particularly a low amount of capital per worker, then the returns to capital, that is the marginal product of capital, are going to tend to be higher, right? And so in those countries that are poor and have a high marginal product of capital, the right types of market reforms or government reforms can allow even small investments in the capital stock to set in motion a period of really rapid economic growth. I think that goes a long way towards explaining the last several decades in a country like China, right? So for some of you that remember your history, China started growing much more quickly after the death of Mao in 1976. So in the early 70s, China kind of transitioned from a collectivist type communist centrally planned economy to one that was governed more by free market principles, right? Private property was allowed, supply and demand was allowed to interact properly. And so that vastly increased entrepreneurial incentives in China during the mid to late 70s. Now, you might imagine at the time, China was a very, very poor and impoverished country. okay? And so they had a high marginal product of capital. And as a result, those small investments in the capital stock set in motion a period of very rapid economic growth as China accumulated capital quickly and adopted those institutions and programs and policies that were in place in the developed world. So China quickly embarked on this phase of catch-up growth, right? And so it's no surprise that their growth rate has been higher than ours in recent decades. Now, one implication of this, if you think about it, is that it stands to reason that China will probably not be able to achieve these super high growth rates indefinitely, right? Even China cannot escape what we call the iron logic of diminishing returns. As the typical Chinese citizen gets wealthier and wealthier, and as the capital stock continues to rise, what's going to happen to the marginal product of those investments in China? They're going to diminish over time, meaning that growth rates of living standards should, in the long run, start to come down and converge to values that you see more like in the United States or Canada or other countries that are closer to their frontier in their growth trajectory over time. So here's a complete 180, absurd question. Can bombing a country raise its growth rate? I'm not advocating that we bomb China. I think that would be a terrible, terrible idea. But I think this question will help illustrate the power of diminishing returns to explain why we see these differences between catch-up growth versus frontier growth. Can bombing a country raise its growth rate? Well, let me show you information from another table, and then maybe you can kind of explain it using the production function as a lens with which to view this data. Okay, here are three countries: Germany, Japan, and the United States. What I show you here is the growth rate of each country in the 1950s and compared to the 1980s. You see that Germany and Japan in the 50s grew at rates close to 7% compared to only 1.2% in the US. And in the 80s, Germany and Japan had growth rates that were much closer to what we experienced in the United States. Now, what do we know happened during World War II? Most of or I should say a lot of the domestic capital stock in Germany and Japan was completely obliterated, right? Does it make sense from the view of a production function then that Germany and Japan would actually experience rapid growth in the decade immediately following World War II? Why? Matt? You had your hand raised? I was going to call in. Okay. Here's Germany's production function, let's say. Let's say in the 1940s they were here. The British and the Americans bomb Germany, and so immediately a bunch of their capital stock domestically goes away. And so they jump from this point, let's say, down to this point on their production function, where the marginal product of capital is going to be higher because of diminishing returns. So then, starting at this lower point, each additional unit of capital is going to increase output in those countries faster than it would have otherwise, right? And so, in fact, this data is perfectly compatible with our understanding of growth from the context of a production function that exhibits diminishing returns. During the 50s, one could argue that Germany and Japan were in this rapid catch-up phase of their growth, whereas by the time they eventually got to the 80s, they were approaching more of the frontier where their growth rates started to kind of converge to what we see in the United States. Now,
Post-World War II, didn't the U.S. also
it did. Yeah, and so some of the reforms that helped promote growth in that country are directly related to us too. Yeah, not just the bombs. Okay, other questions? All right, so moving right along then. That was the first key ingredient then of the Solow model. The production function tells us how capital is related to output. All right, physical capital is related to output. That increases in capital increase output, but at this diminishing rate over time. What I want to do now is switch gears a little bit and talk a bit about where that capital actually comes from. Okay? In other words, we need to think a little bit harder about the process by which the capital stock actually accumulates over time. All right? What is the process that allows countries to increase capital one year to the next? Okay? All right, to understand this, you first have to be comfortable here with the idea, and we've talked a bit about this earlier in the semester, is that additions to a country's stock of physical capital, these equipment and machinery and warehouses, etc., basically corresponds to the portion of our output every year that is saved, or I should say invested in the capital stock rather than being consumed, right? So think about it. Every year, a country produces a bunch of goods and services, okay? We use a lot of our resources to produce goods that we're going to just consume directly. Food, clothing, entertainment, etc. Some of our resources, however, are used not to produce consumption goods, but to produce more capital goods. We call that investment, right? When a country saves, it's ultimately going to, rather than consumes, it's ultimately going to invest in its stock of capital, and capital will tend to grow over time, okay? This leads me to I guess it's my fourth assumption about the Solow growth model, and that is, we're going to assume that the little economy we're describing here today doesn't have a government and also doesn't trade with other countries. So G in our economic model is going to be 0, and net exports are going to be 0. This implies then that a country's output, or GDP, is not C plus I plus G plus NX, but rather it's just the sum of consumption and investment. Okay, so easy example here. Let's suppose that we consume $7 trillion worth of goods in 1 year, and we devote $3 trillion towards the production of investment goods or new capital goods. Then that means our country's GDP is going to be 7 trillion plus 3 trillion, or $10 trillion. Let me define so this is going to be the first little Greek parameter variable in our model, this lowercase gamma here. I'm going to define that as our country's investment divided by GDP, or output, I over Y. That's obviously the fraction of our output that is invested in new capital. In this little example, it would be what? 3 divided by 10, or 0.3. In other words, 30% of our economy's resources, or our economy's total output, is used to produce investment goods and therefore augment the stock of capital rather than producing consumption goods. The fifth assumption in the Solow model then is that the rate at which a country saves and invests, that is this gamma variable, is going to be constant. We're just going to assume that our country, or the economy in this model, saves and invests a constant fraction of its output every period. If you want to think about a period as being 1 year, then in this example, the economy saves and invests 30% of its output every year. And that is not going to change unless we analyze how a change in gamma might affect the equilibrium of the model, which we will do later on. okay? Let me stay on this theme of capital accumulation for just another minute here, because I think it's important to visualize how capital grows over time through investment, doing so graphically, okay? In other words, let's take a look at the relationship between a country's capital stock and how much new capital it adds every year through investment. So again, on the horizontal axis, we'll draw different possible values of capital. And on the vertical axis here, we're gonna look at both output and investment. Now, let me just put the production function that we've already used as an example here. Okay, so for example, if we have 100 units of capital and output is the square root of k, then we're going to produce 10 units of output in our economy. Okay, this blue line right here is what I'm going to call the investment or investment/savings schedule. Okay, now where does it come from? Remember, in the Solow model, investment is a constant fraction of output. So investment divided by Y was equal to 0.3 or 30%, right? So the amount of investment that goes on in our economy then is just going to be equal to 0.3 times output. This parameter, gamma, which in this example is 0.3, then determines how a country's output is going to be allocated between consumption and investment, right? If the capital stock is 100, how many units of investment are we going to undertake then? It would be 0.3 times Y, which is the square root of 100, or 10. And so investment is equal to 3. My graph here isn't perfectly drawn to scale, but this point here is supposed to occur at a level of 3. What is consumption going to be then? Well, it's just the difference between output and investment. So in this case, it's 1 minus 0.3 or 0.7 times 10, giving us 7 units of consumption. So what gamma does, or 0.3 in this example, is it determines how total output is allocated between investment and consumption. Okay, let's suppose that we decide to invest a larger share of our resources, and gamma goes from 0.3 to, let's say, 0.4. Then what happens to this investment schedule? It's going to shift up, in which case we're going to have larger investment but less consumption, right? So that's what that parameter gamma really determines, is how a country's total output is divided between consumption and investment. The last thing I want to point out, and maybe this is already obvious to you, but you'll notice that the investment schedule or curve looks a lot like the production function. It has this same concave shape to it. Why is that? Well, it's because investment is just a number less than 1, 0.3 in this case, times output, which is just the square root of k. So it's going to look like the production function, just rotated down a little bit. Why is that important? Because if the production function exhibits diminishing returns, so will investment. So as countries get richer and their capital stock accumulates, they're going to invest more and more in the capital stock, but they're going to do so at a diminishing rate. So investment is subject to diminishing returns. Okay, questions about that? The third ingredient to the Solow model is what we call depreciation. As a country invests every year, their capital stock tends to rise. However, there is a natural force in the world that causes the capital stock to decline over time, and that's what we call depreciation, right? When a company buys a new piece of equipment or machinery, that equipment is not going to last forever. It has a finite life cycle to it, right? If a business builds a new warehouse, that warehouse is not going to last forever. It depreciates. Perhaps it depreciates more slowly than a regular piece of equipment, but it depreciates nonetheless. Okay? So investment tends to raise capital. Depreciation tends to lower the capital stock. Let me give you a quick example. Let's assume that 2% of a country's capital stock becomes unusable every year because of depreciation. If we have 100 units of capital, then how many units of capital are going to become obsolete by the end of the year? Well, 2% of 100 is 2, right? And so that's going to leave us then with 98 units of capital next period, unless what? We make investments in the capital stock to raise K. Second Greek letter, lowercase delta, I'm going to define as the fraction of capital that wears out every period. I'm going to call that the depreciation rate. So in this example, it's just the amount of capital that depreciates divided by the stock of capital. In our example here, depreciation was 2 units, the capital stock was 100, and so the depreciation rate was 0.02 or 2%. The sixth and final assumption in the Solow growth model is that the depreciation rate is fixed and constant. We're just going to assume here that the capital stock depreciates at some known rate over time. Okay, we've graphed the production function. We've graphed the investment curve or schedule. We also want to look visually at an economy's depreciation schedule. Fortunately, that's really easy to do, because if capital depreciates at a constant rate, then that means the depreciation curve is really just a straight line, okay? So for example, if the capital stock is 100, in our example, we had 2 units of capital wear out by the end of the year because the depreciation rate was 2%. If instead the capital stock were a lot higher at 200, then how much capital would wear out by the end of the year? Well, 4 units of capital, because 4 is still just 2% of 200. What do you notice about the slope of the depreciation line? So 4 minus 2 over 200 minus 100 is 0.02. That's the depreciation rate. So the slope of the depreciation schedule is exactly equal to this fixed depreciation rate in the Solow model. Again, what this graph shows you is how much capital wears out every year as a function of how much capital a country actually has. It tells us something important, though. As a country gets richer and as it accumulates more and more capital, and we move farther over here on the horizontal axis, what's going to happen to depreciation? It's going to rise. And so just by virtue of having more capital and being a richer country, we're going to experience a larger amount of our capital stock depreciating every single year. That means that rich countries are going to have to invest even more just to replenish that depreciating capital every single year or every single period. Okay, questions about that? We've talked about the production function. We've talked about the investment schedule and how that's related to the capital stock. And we've talked about this idea of depreciation. We now want to start putting all of these pieces together to see what the Solow growth model predicts or tells us what's going to happen in an equilibrium state, okay? Understand fully how the capital stock evolves over time, or how it grows, so that we can explain catch-up growth. We need to think about how investment and depreciation impact the capital stock together. right? We don't want to just look at them one at a time. What does investment do to the capital stock? It tends to increase it, right? What does depreciation do to the capital stock? It tends to decrease the capital stock. So in order to determine whether capital is rising or falling, what do we need to do? We need to compare how much a country is investing to how much a country is experiencing depreciation. Now let me ask you guys this. For a very poor country, which do you think is going to be greater, investment or depreciation? Why? Think in terms of the production function. Think in terms of diminishing returns. I want to discipline your all's brains about these types of concepts by making you view the problem through the lens of the model. Yeah. There's not as much to depreciate, but even more importantly, the marginal product of capital is very high, meaning, Matt, that an extra unit of capital is going to raise investment by a lot, but it's only going to raise depreciation by a little. So investment is going to tend to be bigger than depreciation for poor countries, right? What about for countries that have a huge capital stock? In that case, it might be more likely that depreciation exceeds investment and the capital stock will fall as a result of that, okay? Now, let me get back to poor countries for a second. Our model and the law of diminishing returns tells us that investment is probably bigger than depreciation for countries that have very little capital. But what's going to happen over time as the capital stock grows? Investment is going to increase, but Matt, at a diminishing rate. Depreciation is going to increase at a constant rate. Eventually, what's going to happen then? You're going to get to a point where depreciation is now outstripping investment, in which the capital stock will start to decline, okay? Let's put all of that together then on the same graph. So again, we've got capital on the horizontal axis, and then different variables here we're going to look at on the vertical axis. So here is my depreciation schedule. We've already been over that. Our example, we've assumed a constant depreciation rate of 2%. Here is the investment schedule, where again, we're assuming our economy invests a constant 30% of its output into new units of capital, all right? Let's assume we're dealing with a poor country, where the units of capital here is equal to 100. How much is this economy then going to invest in new capital? Well, it would be what? 0.3 times the square root of K. So 0.3 times 10, meaning we're going to invest 3 units of our output in new capital. So all else equal, if we have 100 units of capital and we invest 3 units this year, we're going to have 103 units of capital in the next year. But we've also got depreciation, right? Capital depreciates here at a rate of 2% per year. So 2 of those 100 units of capital become obsolete by the end of the year. And so how much capital then on net are we going to have next year? We've gone +3 for investment and -2 for depreciation. So we're going to add 1 unit of capital to our stock of 100, and the capital stock then is going to move to the right on this axis. Anytime investment exceeds depreciation, the capital stock is going to be growing, like it would be for a country that is in this kind of catch-up phase of economic growth. What if we're talking about an economy that has a much larger amount of capital, let's say 400 units? In that case, and again, I apologize for these lines not lining up perfectly correct, but investment would be what? 0.3 times the square root of 400, so that's 0.3 times 20. giving us 6 units of investment. However, depreciation is 2% of 400, and so 8 units of capital would wear out. So we have plus 6 for investment, minus 8 for depreciation, which means the capital stock is going to be 2 units lower next year, 398. Anytime depreciation exceeds investment, the capital stock is declining. What do you see happening in this picture then over time? Where are we going to move in equilibrium in the long run? To this point at which investment is exactly equal to depreciation. If our country, our economy hits that point where investment exactly balances depreciation, then the capital stock is not going to tend to increase or decrease over time. This point in the Solow growth model is what's referred to as the steady state. This is the equilibrium point in this long-run growth model, where the investment schedule intersects the depreciation schedule. For this model, it occurs at a capital stock of 225. At that point, investment is 4.5 units, depreciation is 4.5 units. All else equal then, the capital stock will tend to stay there over time, and therefore the output will also tend to stay at whatever it's equal to, which is the square root of 225 or 15. As soon as these curves shift, however, you're going to have a movement towards a new steady state equilibrium. We'll do some examples of that in the next class. Now, in the closing minutes that I have here, let me emphasize 2 important points about the steady state. 2 reasons why it is important. It's an equilibrium in the sense that once the economy has reached this point, it's going to tend to stay there, all else equal, right? Again, I like to sometimes just go back to simple demand and supply model. Where is the equilibrium? At the intersection of demand and supply. That tells us what the equilibrium price and quantity are. You guys know from your extensive studies of that simple little model that the market will tend to stay at the equilibrium unless what happens? There's a shift in the demand or the supply curve. Same here. The economy, in the long run, will stay at this steady state equilibrium unless something causes investment or depreciation to change. The other reason why it's important, and I actually think this is more important, is that this equilibrium point is stable in the sense that we're going to converge to this point regardless of where we start. It doesn't matter if our initial level of capital is really low, is a bit higher, or is really high. What does the model predict is going to happen in the long run? If investment is bigger than depreciation, capital will rise continuously until the steady state is reached. If alternatively depreciation is bigger than investment, capital will fall until we reach the steady state. So the equilibrium point here is important because it is a stable equilibrium, that all else equal, the economy will kind of naturally gravitate to this point in the long run. Okay, questions about that one? So this is the main theoretical framework that I want you guys to study and understand. We're going to work some problems in the next class, and the Excel extra credit assignment will illustrate the dynamics or the mechanics of this model, hopefully very intuitively for you, all right? But this is the setup that I want you guys to understand. The production function, which I haven't actually graphed here, the investment and depreciation curves, and this concept of a steady state. Matt? I might ask you to find the value of it, or I might ask you just to graph it conceptually and discuss what would happen just kind of descriptively. Would it go up or down? So here's a good, let me answer your question this way. In the last couple of minutes I have, we'll just work this one together. This active learning exercise is the exact same problem we just did, except with algebra instead of graphs, okay? Let's suppose I give you, Matt, on an exam, this production function, y is equal to the square root of k, and I tell you that the depreciation rate is 2% and that the savings investment rate, gamma, is 30% or 0.3. Can you compute then numerically the steady state equilibrium values of capital, output, consumption, etc.? Should be able to do that. Now, how do we do that? Well, on the graph, where did we locate the steady state equilibrium, Wyatt? The intersection of the investment schedule and the depreciation schedule. Algebraically, you do the exact same thing. You find the point at which investment, which was gamma times the square root of k, that's output, gamma times y, is equal to depreciation. That is the depreciation rate delta times k. That's all that equation says. That's a statement of the equilibrium condition. Gamma times the square root of k is equal to delta times k. Now you just got to do a little bit of, what is that, algebra 1 or 2? I don't remember. Divide both sides by the square root of capital and divide both sides by delta. You get k over the square root of k is equal to gamma over delta. What's k over the square root of k? You subtract the exponents, right? So this is k to the 1 divided by k to the 1/2. So that's just k to the 1/2, right? And then how do you turn that into a k? Then you square both sides of the equation. So the capital stock is just gamma over delta squared. So Matt, if you know gamma and delta, you just plug those values in and you find the steady state value of capital. It's 225, which is exactly what we saw on the previous graph. What is the steady state value of output? It's just the square root of capital. 225 square root is 15. What's consumption? It's just 1 minus the investment share, 0.3, times output, or 15, giving us 10.5. Investment is 0.3 times 15 is 4.5. Depreciation is the depreciation rate, 2%, times the capital stock, 225, 4.5. It is the exact same concept that we did graphically, but with just a little bit of algebra here. So I could ask you this type of problem either way, but it tests the same concept, right? The key concept here is that in a steady state equilibrium, investment is equal to depreciation. And that's where the economy will tend to gravitate to in the long run. Here's what we're going to do in the next class. We're going to add to this model just a couple of little features to help it kind of distinguish between this catch-up growth, which is about countries accumulating physical capital towards the steady state, versus frontier growth, which is about improvements in the state of technology. We'll do a couple of examples together to show how we can manipulate the graphs to kind of discriminate between those two types of growth experiences. And then I'll allow you guys the rest of the time to begin work on this extra credit assignment. Okay? That's it for today. Please read the stuff online. This material is a little bit harder, as you are aware of now, than some of the other stuff that we've been doing, okay? Yeah.